and put a message in your respective chat channels letting me know that you can hear, and then in a second, hopefully, let me know that you can see. Let's see, I'm going to go ahead and start sharing the screens. All right. Whoop. Screen sharing is turning on slowly. Let's see if Discord wants to cooperate this morning. Discord land, somebody can shoot me a message and let me know if you can see, hear, well, you can hear at least. Wafa, can you see anything over there? Can't see anything yet. One moment then. Get this taken care of. While that's happening, let's see. Oh, one thing that I should say to you guys over in Discord is that there's a reason that we started preferring the webinar platform, and there it is. If you want to jump in, you can join over on the webinar side. Discord is a fickle mistress at times, so I'm going to come back around and see if this is going to work here. Zach, while I'm doing this, you want to say hello to everybody?
Hi, everyone. Can you hear me? Am I muted? You can hear me.
I think you should be good.
Yeah, cool. Hey, everyone. Hi, I'm Zach. Happy to be here today. Awesome. I'm really looking forward to experimenting with FreeRTOS today and using it for AI applications. I need to put it on this screen so that I'm looking at the right screen.
Well, cool. Thanks for covering for me. All right. How about now? Those of you in Discord, can you see the stream? Wafa, any of you folks over in Discord land? Great. Perfect. Wow, we made it, guys. All right. So anyway, for everybody, oh, here's Wilson trying to help out. Not today, Wilson. So for everybody who's joined us, thanks a lot. We are back with another edition of Engineering Hour on TensorFlow and FreeRTOS. So this is a series that has been about how you can use an RTOS to build embedded AI and machine learning applications. In Discord, I already dropped a chat that has a lot of information about different sessions that we've done up to this point. I think we're on session 4 or 5 now, maybe, of this series. But you can check those out, and in the virtual event platform, those links are coming shortly. A quick note for those of you who may be in the virtual event platform, aka not Discord, but have never interacted with the DevHeads community before, I just put in a link to our community. Zach, Amesh, Ming, tons of other Hemel, tons of other experts in embedded and IoT device development hang out there. So if you're working on a professional project or even just getting started, feel free to jump over to https:// discord.gg/devheads and there you'll find all these guys and a bunch of other friends who are like-minded, and hopefully you can find some collaborators and get some cool stuff built. Anyway, today's session is going to be about 45 minutes long, and during that time, Zach's going to be using lightweight ML models to process sensor data in real time, and we're going to learn how AI allows us to make smarter decisions on resource-constrained devices. And then at the end, we are also going to do some Q&A, so if you have any questions during the course of the event, or now for that matter, feel free to drop them in to the chat channel. If you're reading anything that I'm putting into the respective chats, that's the chat channel, so you're already there. A few things that we have to discuss today before we get going are housekeeping and self-help. Again, I'm posting this stuff into the respective chats. But the housekeeping and self-help are to make sure that you, if you have any issues with the stream or you can't hear anything, you have some recourse that you can take on your own. So the first thing is check your bandwidth. If you go to a service like speedtest.net, you'll be able to see how much bandwidth you're pulling. And if you're pulling less than 5 megabits per second, you may have issues. So in that case, try to go get to a different network if at all possible. Number 2, try quitting the application you're using and coming back in. This isn't really for the virtual event platform, hence the earlier comments about why we switched into the virtual event platform. It's mostly a Discord comment. So if you're using Discord, try quitting Discord and coming back into the session. The other thing about Discord is we've found that using the desktop or mobile apps is sometimes finicky, so you're going to have to make sure that you're using the most up-to-date version. So rather than that, I would suggest that you use the web app, and again, https://discord.gg/devheads, and then navigate over to the Engineering Hour channel, and that's where you'll be able to tune in. Some other easy things: close anything else that may be consuming bandwidth, close any other applications that may be consuming a lot of memory. There is a link, as I said, in Discord now to the virtual event platform, so you can hop in there. And then if all of that fails, DM me. In Discord, I'm at TechieLou. In the virtual event platform, I'm at Brandon Lewis, and I'll help you out with any issues as much as I can. Other than that, we are recording this, and we're going to be replaying it next Saturday during the Engineering Hour reheat. That's going to be pushed out over YouTube. It's going to be pushed out over LinkedIn. So there is another opportunity to see the content from today if for some reason you were unable to view it. And Zach today, like I said, is going to be doing this for about 45 minutes. Put any questions you have into the chat channels, and we'll get to them as we can, and then feel free to continue the conversation in the server. We always encourage that after the event is over. Other than that, I think we're about ready to get going. There will be another wrap-up session on this series in about a week, but we'll let Zach take us from here up until that point. And Zach, I think if there's nothing else, we are probably about ready to go. I think it's your turn.
So, sure. Let me share that screen, and then we'll get on it.
Yeah, and once you share, let me just confirm that everybody in Discord land can in fact see. And Wilson, I'm going to banish you from the stage. Don't try to rejoin it, please, for the love of God.
He's eager. Okay, cool. Hi, everyone. While Brandon makes sure there's people on Discord and they can watch, I'll do a quick introduction. So, hi, I'm Zach, and I'm one of the. Let's play that so that it's a good. Let's do a slideshow. Cool.
Looks like good to take over. It looks like everything in Discord's working, so I'm out. Good luck.
Cheers. Thank you. Hey, everyone. I'm Zach, and I'm one of the people who hangs out on the Discord, and I'm really glad to try and do a demonstration of AI with FreeRTOS and TensorFlow today. However, today's presentation is going to be more about a battle of attrition with combining various systems together, because as you have seen in previous weeks, really, we already have the whole application working. In the previous session, we showed you how to build a model, I think, and train the model, and then we also showed you how to collect data for the model and how to feed the data into the model. And then after that, we built the model and we converted it into a light, or rather a TF light, or even more than that, a flat buffers format. A flat buffers format is how you need to represent AI in a model. A model is a really huge collection of code and collection of connections. It's basically a table that connects a few things with each other, rows and columns. It's a very large one. Now, in order to use a model on microcontrollers, you need to do something that's called quantizing, which is kind of you're basically running a compression algorithm on the model and making it as small as possible, but with as much accuracy as possible. So last week, after Wafa had prepared our model and she had minimized it, we ended up with a model that was 83% accurate, if I remember correctly. And we had collected data with it with our physical hardware, which was the MPU 6050 running on a STM32F4. It's right across of my screen here. So we've collected the data, we've trained our model, we've now minimized our model into a smaller model that can run on a microcontroller. Now we sit on this land where we have to we need to put in the libraries, or rather the APIs that enable us to use the model to infer. And what is inferring? It's basically, if you train the model on images and you want to recognize, say, eggs, you give it images and you let the model give you a probability on whether there's an egg in that image or not. The model doesn't really do everything for you. All the model gives you back is a list of probabilities, and then from there on you have to take these results and build them and decide on your own whether this means it's an egg or not. Okay, so what are the advantages of doing this on a small device? Why would we go through all the trouble of making the model less accurate, making the model smaller, the trouble of building a lot of code? That models are built in Python usually, and firmware is usually built in C or C++ or something like Rust. Why would we go through all the trouble of combining all of these things? And the reasons for this is, so the first reason being running systems as close to where the data is produced, basically at the edge of our operations, is much faster, because we remove a round trip of sending data all the way to the server and and then having some process run on it and then getting a result come back to us. The second one is it's more private, because the data never travels off of the device. So you're already protected against things like man-in-the-middle attacks and people like sniffing on your data, and as well, you can deliver value. You can deliver what your machine learning does without connections, which means you have better battery life. You have more space to write other code, more space to store artifacts and things of the sort. And you can envision an operation where you do a lot of machine learning locally, and then at points where you are connected to higher data, you can then, at those points, you can sort of do more like a quick exchange with data with the server. I remember in Android development, we used to do that a lot. You would do as much as you can locally behind the views, and then whenever you would get a big network boost, for example, if someone who's running your game would jump on Wi-Fi and you would sense it, and then you would download updates and such, and you could do some sort of connection like that. Have a tiny device that basically has no connection until they connect to a bigger device. And when the bigger device is connected, they have some data that goes to the cloud. But running machine learning on the edge avoids all of that. So you can deliver value without needing a connection. The other thing is, without building as much connection pipelines to move data orchestration through your IoT system, with things like, I guess, Seco, things like IoT platforms where you can connect your gateways and then all the data can go up and such. And a lot of the times, this used to be how we used to run machine learning. You would collect data at the edge, you would save it, and then you would send it to the server, and then the server would do it. But now with tools like LiteRT and TensorFlow Lite, we can run inference, or rather run machine learning on the remote device, or the devices at the edge. And then also with tools like LiteRT, we have compatibility with wide devices, all the way from like desktop or microprocessor Linux and Windows and Mac devices, all the way down to microcontrollers, 16 and 18-bit like microcontrollers with like 16 KB of memory. You can do such a wide spectrum of machine learning that if you have a heavy application or a heavy application set that delivers this kind of data, you would really have an advantage of running it all across your system, which means also at the edges, basically where the last mile to the client. Okay, so let's speak about this. This becomes the crux of our issue, and this becomes one of the reasons we're going to look at the code, but we're not going to run it today. So whenever you're building machine learning, you have a lot of wide tools. You have your model, number one. The model is built in Python. And then you're going to have things like your HAL or your Cortex microcontroller software infrastructure, KIMSIs basically. You're going to have things like KIMSIs. And then in this particular example, we have FreeRTOS, which is another set of libraries that lives by itself. And then as you see, as I explained to you, you're seeing we have tools written in C++, we have tools written in C, we have some other tools written in Python. And then now, when it's just C or C++, it's quite easy to trade in between them, because you're just basically, at the end of the day, you're using the core C standard library. But once you start adding other tools, like what the models bring in, which is all the rules and all the sets and all the inference things where you have to do the actual machine learning, and you need things like NumPy, and you need things like scikit that have been sort of translated into C, but not exactly. So you need to be able to build distinct packages. You need to be able to build your firmware separately. You need to be able to build your real-time operating system separately. You need to build your register or your HAL provider, KIMSIs basically, separately. And then you also need to build your Python or your model code or your model quantization, which will look like a C library, but under the surface, really, quite a bit of that code is Python, and some of it not even Python. So you suddenly end up in a situation where you need to deliver one thing, but it is built in very many different situations and very many different toolchains. And then as you have a very wide variety of the way things can go wrong. And basically getting the compilers and linkers to share all the right resources becomes really difficult. So what's the solution for this? We've tried it for quite a while. I and two others in the group. We've tried it for quite a while, and at the end we came to realize that there's tools that have been built for these solutions, because previously there was hacks of how to do this, but the hacks in the end never really delivered machine learning at the edge. It was almost machine learning at the gateway level. So the first sort of embedded Linux device in your IoT infrastructure, lower than that, no machine learning, higher than that, machine learning. So now we have, in this day and age, we have something called Bazel. And Bazel is a tool from Google that allows us to build our multi-language, multi-platform project. So you're building a project that maybe contains a lot of languages, As in our case, we have C, we have C++, we have some Python, we might have some Java somewhere in the libraries that we're using. We're not aware exactly. The TensorFlow is quite a big library. And then you start realizing you end up in this situation where you can't build all of your code and you can't join it at once. And then you find out about this tool that's by Google, which is an open, it's by the Google Foundation. Can I call it the Google Foundation? By the Google Group, but then it's an open source build project. And it's designed for you to use with projects that span different languages and span different build architectures. So things like compilers. You have one project, but there's parts of the project that are different, built with different compilers. You have one project, but parts of the project are built with different languages, sometimes different languages and different compilers. So if you have problems like that and you need to deliver that collection of information, if you've done any sort of web development, this starts to sound very familiar with backend and frontend and all of that, and CSS and such. So Bazel helps us in this quest by, number one, it only builds what is necessary or rebuilds what is necessary. If you've rebuilt a project and then only 2 source files have changed, we can reuse all the other build material without rebuilding the complete project. So, and then you find you can now start doing things like your machine learning can change, but as long as your firmware and your HAL and your other tools have not changed, you don't need to build them as well. And then you're building and testing multiple languages to be in one go. Basically, you have one build command, and this build command allows you to go and say, build Bazel and build, and you can run all of these sub builds for you. The trick now becomes that as you're setting up the building across your system, you will realize that you have to set up rules that go for each language, rules that go for each binary, rules that go for each platform. And these rules are quite like intricate to build, and that becomes where the project sort of becomes hairy. If it was just a C project and you are only using C, Bazel becomes really easy to use, easier than CMake because you can almost just use it automatically. Or if it was just a Python project, it could be easier than pip because pip requires a different repository, dependency structure, and Bazel is very good at dependencies. You can either supply actual dependencies that are local to your system, you can supply them from source control, you can supply them from some sort of Docker repository. It depends on how you're using them, really. So it's quite flexible in that respect. And then you can use Bazel from little scripts to giant code bases. I think someone was telling me that all the big C libraries, I think standard and quite a few of the libraries are built on Bazel. And that's basically what people, it's a trusted tool it's a trusted tool for today's multi-language projects. Okay. Cool. Now, the next part, you need to, if you end up in a place where you're doing some sort of scripting that is not supported by Bazel, you can advance that with Bazel's own language, which is something like BlastRack or something. Sorry if I've mentioned that wrong. But you can extend Bazel so that it accommodates your new languages, your new rules, your new sets of organization and as rule, pre-built tools. So whenever you're doing pre-CI stuff, you don't want to end up with null pointers in CI. So you could add rules to make sure that some tests are run locally before the code is submitted and pushed and such. So that's what Bazel does for us. Cool. So let's look further and I'll explain. So after building, which we'll look at the code, we'll shortly look at it right now. After building the code, we are able to combine all of our sources and all our breakdowns of little packages. So the TensorFlow package, and then the firmware package, and then the HAL package, and then the real-time package. Now, what do we do? Our code is building. We have all our code touching each other. What do? We need to go back and combine the data the way we saw last week. We saw last week, we were moving the sensors in a circular manner, and as we were moving the sensors in a circular manner, we could collect the data of the accelerometer and of the gyroscope, and those pieces of data came out in quite a varied form. So it isn't just that we need to collect the data and then give it to the inference tool or the inference library and it will reply. Yes, you can use Bazel as a replacement for pip-waffle. You can use Bazel as a replacement for quite a lot, almost any build tool that you're aware of right now. So as we were collecting the data for machine learning last week, we realized that each movement will come out with a multi-dimensional array. So each gesture that we try and sense, which is say like a circle or like a square or like a rectangle, each movement that we try and sense will come with multiple X data, multiple Y data, multiple Z data. And we have two sets of X, Y, and Z. We have X, Y, and Z from the accelerometer, and we have X, Y, and Z from the gyroscope. So how do we, yet when we are giving the data to the inference tool, so to the machine learning tool, we need to give it one piece of data for X from the gyroscope, one piece of data for X from the accelerometer, Y, Z, all of those, each. So it needs to be one row of data rather than multiple rows and multiple columns of data. So once we collect our sensor data, which is how the shapes are being drawn, how fast the accelerometer is moving, how fast the gyroscope is losing balance and gaining balance, we need to reprocess that data. And what that looks like is you need to do something that is called standardization or normalization, where you compress multiple pieces of data into one piece of data. And that looks like you get a standard deviation on an array, and then you get a mean on the array, and then you divide the standard deviation by the mean, and you by doing that, you compress the data to one. It's basically called normalization. You now have one piece of data to represent the whole column of data. So now you have one piece of data to represent them. And if you do that across 6 axes, you have 6 pieces of data, which is a row of data. And then now once you have this row of data, you can pass this row of data into TensorFlow, and then TensorFlow would now log back whether there's enough probability that this is a shape you recognize, and if it is a shape you recognize, which shape it is. So you could end up doing some sort of thing that looks like an ellipse. And then if you don't have an ellipse, I could imagine that you would have something like a small probability that says this is a circle and a small probability that says this is a rectangle. And depending on how you've set up your code, you can break it down so that your code starts to decide this looks more of a circle, this is more acceptable as a circle, or this is more acceptable as a rounded rectangle. Or if you've trained your machine learning with that much data that you can differentiate the curvatures of the ellipses, then you might be able to even recognize the ellipse itself rather than it being a circle or a rectangle. But the results from the machine learning model will always show you a list of probabilities. So before we jump into the code, I'm going to look at the questions and then we're going to start looking at the code. Okay. Hi, everyone. And if you have any questions, as I put up my VS Code, you can start asking. That's good. So, as I explained, here's our code, and we have the drivers for the 6050 We have the, okay, Puneet is typing. We have the I2C driver. So this is all how it is connecting. And now you start to see, please share the GitHub. The GitHub link to this repository is here. So fair warning, this repository is not going to build at the moment. And the reason for that is we still need to finish the conversion to Bazel. So I will share the link here. Okay, cool. So we have all the drivers in the code. We have all the drivers in the code, and we have the code that is supposed to read. But the reason we see all these red lines is because our build is not working at the moment. And in a couple of days of trying, the difficulties that we've faced so far is getting the Bazel to give us the correct rules for our STM32. We're going to work on this more after. The code is live, and the code will be available for everyone who wants to play with it. So the thing I can encourage you is to watch the repository, and we should be able to finish this soon. But if you go through our code, all of it is broken down, all of it is explained. You can go through and see how we are reading everything and how all the functions are handing over data to each other. You can see how we are doing the quantization, and you can see how we're doing all the breakdown. The difficulty with getting all of this to work together is because you have, first of all, KIMSys, you have FreeRTOS, you have all the data that is going into the model itself, which is not in this repository. Wait. I will share the code with the... Okay, so there's two repositories you need to look at. I'll share the other one, the machine learning one as well. Where is machine learning? Yeah. So there's this repository as well. This repository contains the machine learning code for our project. I'll open it just now. Yes, Open documents. ST workspace training with okay, cool. So in here you will see that we have basically there's a README that explains all the files in here. So just a moment. Oh, yes, I translated that. Okay, cool. So there's a README that explains all the files in here. And the model that we're using, that we're referencing from our code is here. This is our TensorFlow. This is how it looks like. It's a huge, I'm sorry. Let me try and, can I open this as a, yeah, sorry. So I need to open this to the hex editor. So this is a model. This is a model this is the model that contains all the logic that is used for running inference. And inference is when you join data with the model. So if you want to recognize a shape, so if you want to recognize something like a shape that is a circular shape or a rectangular shape, all of the code is compressed into here. And this format that the code is in is called flat buffers format. it's a format by Google, and it basically helps to quantize large amounts of data by compressing them into smaller flat structures. Now, in our microcontroller, whenever we collect the data and we compress it, we need to pass it into this model, and then once this model has it, this model can now give us back probabilities on whether is this shape that we recognize or is this a shape that we don't recognize. Okay. Now the difficulty becomes this model is built on basically is built on a Python is built on a Python architecture. So all of this is built using Python. All the code is there. You can go through it. You can build this model. You can train this model to do something else. But all of this is built using using Python. However, all of our firmware is built using C. In order to make these two to work together, it's necessary now to have a build tool that builds the C separately and builds the Python separately and joins them. And this was the difficult part of this, because it's quite easy to build all of this, to build the firmware so that it reads, quantizes the data and breaks it down in a way the model can understand. But now when you get to handing it over to the model and using it, yes, handing it over to the model and the model doing inference, it becomes difficult, because now you need a build structure that can handle both C and Python. Separately, they're easy enough. Together, we need to learn a new build structure, which I hadn't used yet, which is Bazel. And that has been the difficulty that we are basically facing right now, and will keep on until we get it done. So with that, I want to invite questions. We know the locations of all the files. We know everywhere to try. I'd like to invite questions to what we're trying today, and I know most of this can appear very confusing. I might need to repeat it a few times. So I think I'd like to see what questions people have. Let's see.
Yeah, specifically, I know that Asraful Wafa, based on our previous sessions, have been involved in the development of this project. So Asraful Wafa, by the way, there's an STM32 microcontroller here. Have Asraful and Wafa been using Bazel? And if so, they haven't used it yet, at least you?
No. So Bazel, this is kind of the issue. Bazel comes up only after, as you can see from Wafa's code here, she's using pip, because she's in pure Python land. There's no need to use. She's only writing Python, so she doesn't need to use Bazel. And then in the firmware that I and Asraful have worked on, we're only using C. So there's no need to use Bazel as well there. But when it comes to you doing the both together, remember, for data collection, you're not running any machine learning on the device. What you're doing is just you're collecting the data and you're logging it to a certain, you're basically making a row of data and labeling it on whether it is a circle, or is it a rectangle, or is it not a shape. You're not using any machine learning. You're just collecting data and labeling. So there's quite a few code bases. There's a code basis that uses the sensors to just collect the data and read it and quantize it in a way the model can understand. There's a data set. There's a code repository, the Python repository, that takes the code, takes the model data, which is all the movement data, and uses it to train the model, to ask the model, to teach the model, this is a circle, this is a square, this is a thing. So all of those are written in different places. However, now when we get to the last part, the ultimate part of this, now we've collected the data, we know what we want to recognize, whether it's eggs or not. That's easier for me to say right now. And then we've trained the model. The model knows an egg. It doesn't know what it knows what is not an egg. At the end, we need that model to run on a microcontroller, and that's when the problem of Bazel rises. Basically, the person who sits at integrating both of them is the one who ends up with the Bazel problem. I don't know if that explains it.
Yeah.
No.
So my follow-up question is then, I mean, our friend, as we know very well from our friend Christoph from Embeetle, his development environment is designed for microcontrollers. So you're using an ST target. Is there anything additional that you see potentially coming down the pike in terms of optimizations for like a small footprint, small memory target when you're using Bazel, or are you going to have to like extend the tool chain?
No, no. I think it should cover it. Like so, but when we encountered Bazel, especially Taj and I, Asraful and I, and that's one of the reasons where it is whenever if you're using Bazel for one thing, it's very straightforward. It's basically C, but C with dependencies, which I don't know how to explain, but adding libraries to C is one of the biggest baits. So that's why there's a lot of tutorials, including even by me and I think also by Umesh, on how to integrate something like FreeRTOS into your project, because that's adding a library. But now Bazel, which is such an old project, and I hate to just have discovered it this week, is Bazel does dependencies for you. And it also does dependencies from different languages or different architectures. So you could be on the smallest PIC thing, pick microcontroller, and you could still use Bazel without needing to extend it, because you tell Bazel what it's a build tool. You tell it what compiler to use, you tell it what version of the compiler, what runtime to use, where to get which library, and you tell it it makes you label each little thing you use as a package. So the runtime you get from PIC, you label that as a package. FreeRTOS, you label that as a package. TensorFlow, you label that as a package. If you're using ARM and you end up using KIMSys, you label that as a package. So it's already made so that you can make very small and efficient build material. So ST is not so big in the way I'm saying. Basically, what I'm saying is it can work on the smallest architecture possible. I'd like to try it on the what's the Beetle board. Should work.
Yeah, the tiny scarab. Yeah.
Yeah. The one he makes. Yeah, because it's small, yes, and it's also a RISC-V product. So it should still work, because you can tell Bazel which linker to use, which compiler to use, and suddenly you're working on custom hardware. Yeah.
So what's next? Obviously we've got a little bit more integration to do here, but I know you said that, but let's just like in very clear next steps. What are we going to do after this?
In all honesty, we were going to do a recap, which is you want to look. This process has been quite long. It's been quite drawn out. And the reason it's been quite drawn out is because we've attempted to do an industry project in like a few short sections. So we've gone and we didn't use a pre-trained model. So we use our own model. We made our own model and we trained it to do our own thing. And we did that as an exercise to discover all the steps that are involved, because whenever you do get your client and their client wants you to build a medical AI device, there's not going to be a pre-trained model for that. You'll have to train a model to do the thing that you're going to do. If there's going to be a pre-trained model, that wouldn't work with you. So we did that. And then now we're at the point where we've trained a model. We need to make the model smaller and add it to our firmware. Once we add it to our firmware, which is in the next few days, and once it's added to our firmware and it's working all together, we need to look at the process from start to the end. And then that process, the recap of the process of remember when we did this, remember when we did this, remember when we did this, becomes a manual on how to build real world AI applications, because this is what is going to happen. If I mean, if we wanted to show a running demo, we could just run one of the Bazel demos, which just builds by itself. But that would be another demo of just a demo. But we needed, most people want to know, how do I build an actual application? And actually, I think even you've asked before, an actual non-vision AI application, like not the hyped up AI. How are people using AIs in smartwatches? How is Strava recognizing that you're running, swimming, doing fencing? How is Strava recognizing things like that? Because that's a real world application in the wild, not identifying eggs, which is as well, but that's it's a contrived example. This aimed to be a more practical example. And I think next we do a recap of, like, because in the last week when we presented last week, and if you remember, some of the code wasn't working that well, but now it's working. And I think if we have a little bit of more time, we'll make it work and everyone can see it work. It's living on our repository, and it is living code. Which means it's changing. It's not like just there and this is the version that you have from 4 years ago. So the next thing we need to do is recap this and basically end up making a manual of how to build AI applications in the world. That's my very simple, direct to the point next step, I would say.
So I'd like to hear from those of you in the audience. You know, who do we got here now? We've got Peter, Electrogix, Puneeth, Aravind, you guys, Amal, Ben. I'd like to hear from you guys what you'd like to see out of the sessions, and then if you have any questions or places that you need some clarification in terms of you know, what's going on here and places where you guys need help. I think that would be awesome feedback and help us guide our content roadmap. We're building that out for 2025 right now. At the same time, you know, Zach, you were talking about presentations and demos. I do think getting this over to a target and seeing you know, what we've got would be a really cool way to culminate this. Any plans to do that perhaps in the next session?
Yeah, we can do. It should be up before the next session. We can add a video. The problem is there is a target here, and I can put it just doesn't build. So I can show you the thing, and it has its code in it, but it's not doing. It's not just building. So, but the best thing would be expect a video during this week to show you how all of this code is working together, really. And you can ask as the week goes, you can ask about the video and you can ask questions about what you're discovering in the code. Yeah.
Perfect. So yeah, you guys in the audience right now, throughout this process, I know some of you guys have been here for the duration. You know, what are the areas that you guys are struggling with or would like to see? Any of you guys who are in the chat.
I'd love for Peter from Switzerland to give a review because it's come to all of them, to be honest.
Yep.
I'm sorry for calling you out, but I would really love for you to say, we'll take all criticism, well deserved. I'm risking it all by doing this, but yeah, we'll take it. Yeah, I'd love for that to hear what someone says has come to all of them, for sure.
All right, checking over in Discord. Anybody over here? Marvin, anything? Okay. All right. Well, we are at, we've gotten to about 10 minutes within the rest of the session. So I think, or 10 minutes within time. So I think we're about good. Obviously, if you guys have any other questions, you can always hit us up in the DevHeads Discord server, which you can find there, discord.gg/devheads. If you're not a member yet, we will we'll be there to help answer any questions. The other thing is, If anybody's interested in doing this specific project and documenting it in the server, documenting their experience, we'd be happy to ship you guys aboard. So ping me in the general chat and let me know, and we'd be happy to shoot you over a kit so that you can build this, and then let us know your experience and tell us where you're having potential issues or challenges or places you need help. So yeah, other than that, we want to thank all you guys for attending today. Good stuff as always, Zach, and we will see you in the server. Oh, wait, one second. Beneath at the 11th hour. Can we please go over the top level architecture on how we use data received from microcontroller working with this TensorFlow model, basically the toolchain part?
Wait, so do you want to know how we use data received from working with this TensorFlow model? Do you want to know how we are inferring or how we are training? I can do both. So okay, there's a detail coming. Cool. Both please. Oh, sure. So whenever you collect, I'll give you, I don't know how to, so look at it, if you look at my screen, I'm holding up my phone. In my phone, we have a inertial measurement unit. And an inertial measurement unit will have a gyroscope, which measures balance. Is this thing, which is this it this way? Is it this way? Is it this way? And then what is it called? An accelerometer will measure, am I moving this way? Am I moving this way? Any motion, okay? So motion and direction. Gyroscope tells us the amount of direction, or rather the direction we're going. And then the accelerometer tells us what speed we're going. So that's number one. We have two things. One thing tells us the direction, and the other thing tells us the speed. However, whenever we have a few more degrees of freedom. We're not on a Cartesian plane. We're not X and Y. There's also the Z motion, or rather, it depends on how you do your axis. But what I'm trying to demonstrate is we have on the gyroscope for direction, because you can move this way, direction can, you see, there's so many directions and they're not on a flat plane. So whenever you measure a direction, it will come with 3 axes. Whenever you measure a speed, it will come with 3 axes. So it tells you to which side the device is really moving. Okay, so that's number one. Now, when you make a circle like this, okay, you basically make, if you make a circle like this and you do some sort of testing of, you test it at such an amount, let's say you test it at 50 hertz. 50 hertz is 50 times a second. Cool, I think so. Yeah, so you do a circle at 50 hertz. If I say 1/1000, I did 1 second. So we have 50 measurements, 50 points at which we measured that circle. Now, number one, remember where we started. Each point has 3 points, an X, a Y, a Z for the accelerometer, an X, a Y, a Z for the gyroscope. So direction and speed. Now, if you do that, what you end up with is end up with 50 times 3, 150 points. However, whenever we are handing the model, the training data to the model is done in CSV. And whenever you're training in CSV, each row needs to represent one shape. So whenever you're doing this circle in a CSV, it should be one row. But this circle in reality is 150 items. So it's six rows, and then I think however many columns, so that you divide them and you leave them as such. So there's the 3 from the gyroscope and the 3 from the accelerometer. So how we handle 6 rows and 50 columns? Yeah, sure. Yeah, but that would be 300. My math could be wrong. Whatever. But the essence is you have many values for X, you have many values for Y, you have many values for Z, and then you have them twice because you have a speed and a distance. So in order to make those many rows and columns into one row, you need to do normalization, which is just statistics. All of machine learning and digital signal processing and AI is just statistics and probability. There is 90% chance this thing is an egg. You've showed me 5 eggs in the last 4 moves. So there's 1 in 4 chances, the probability is in 1 in 4 chances that you will show me an egg again. So all of machine learning is just statistics and probability. And in order to normalize, which is a term, to normalize data or to standardize data, you'll need to take so for all the AX values, you'll take the standard deviation of all of those values, which is 1 value. And then you'll take the mean, which is another value. And then you'll divide the standard deviation by the mean, which will give you 1 value. Okay. And if you do this for all the 6 rows and the other columns, 6 rows and 30 columns, I'm so confused. Why is it 150 in my head? And 6 times 50 is 300. 6 times 5 is 30. Yes. So for all of those, for that row, for the group of 300 values, you would basically compress them into 6 values. And these are the values you would give to your machine learning model to train it, to teach it. Training is teaching it, this is a circle, and this is not a circle. Okay? That's training it. Teaching it, this is a circle, this is not a circle. And then we get to the other end of the spectrum. You've trained your machine learning model. It is running on your tiny microcontroller. So it's running on your tiny microcontroller, but it's in the field somewhere. The aim of this project is for us to do a circle and to have an LED blink. That's the aim of this project that we're doing right now. And I'm so ashamed that I'm not showing it. To do a circle and to have an LED blink, and to do a square and to have a different color LED blink. So when you do get to that point, you need to do the same stuff. You need to collect all of those points. So you will have something like an interrupt with a threshold, so that you know someone has started a parabola or a curve to show the curve that the curve has started. And then you'll wait until maybe you say per second or something. So if I'm drawing a circle, I have to do it in a second. So I can't do and then talk for many minutes and then do it. So you give it a second and then you measure all of that. And then you do the standardization and normalization again. You end up with 1 row. And this row of data is what you give the model that is running on the microcontroller. And then that model will reply with probabilities. It will never say this is a circle or not. All it replies to you with is a list of probabilities on whether, there's a 50% chance this is a circle, there's a 10% chance this is a line, there's a 4% chance this is an unrecognizable shape. And then you will decide, based on those probabilities, whether your application wants to recognize this as a circle or as whichever shape that you want. Must have been confusing, but I'm hoping that was a little clear. So you have to do standardization and normalization when you're handing it to the model to learn, and you have to do standardization and normalization when you're handing the data again to the model, so that it can infer or predict what shape or whatever, if you're recognizing eggs or you're recognizing squares or you're recognizing colors, whatever you're recognizing, you'll have to do standardization and normalization so you can do it again. You can give it the data back. It's basically the same process when you're going to train and also when you're doing inference. Maybe when you're doing inference, you'll be a bit more tight, and because you're running on a smaller device on a battery and such, and you'll recognize much quicker. Puneeth, does that make any sense?
Yeah, Puneeth is on stage right now. I'm going to ask you to unmute your mic.
Unmute. You can ask questions.
And
yes.
then we can do it in real time.
Yeah. Yeah. Wilson has also been jumping on stage. Does he have something to say?
I think he just wants the FaceTime. He just wants to flash his name. Anybody else? Any other questions? Puneeth is typing again.
I have a question.
Okay, go for it, Wilson.
Speaking about, I have no deep idea about this AI stuff with controllers itself. But can we use the algorithms, the learning process for the machine learning for low-end controllers, for example, like the M4 or the F103, STM32s, or it has to be high-end controllers itself?
So, sorry, can you repeat that? You asked if you can use this machine learning on M4 controllers?
Yeah, like the Cortex M4 or the M3, like the F103, C86, popular blue pill, or let's say the Cortex STM32 Cortex M4 controllers, or must it be high-end controllers that can process the algorithms itself?
Yeah, so I think Zach's internet just dropped, but I'm going to invite Taj and Wafa. I think, Taj, you might be able to speak to that a little bit. Asraful, the application of ML on M4s. I think the answer is yes, but I want to hear from the horse's mouth. He's getting ready to join. Just 1 second, Wilson. There's another question about edge impulse.
Am I audible?
Yep, we can hear you.
Okay. So yeah, it is totally possible. Even we are doing it into Cortex M4, but to use machine learning, you have to check about two things. One is the memory capacity, because if you see, we have trained a small model, and the size of it is around 50 KB. It's really a small model. So if you compare a larger model who is of more accuracy and more data, it can be a lot bigger than this. So in that case, memory is your first concern, and then you can also look on the clock speed. So if your microcontroller is running really slow, like for example, if we took consideration the clock speed of Arduino, which is most of the time 16 megahertz, then it will cause some issue, because you need really fast processing speed too. So
So if I get you correctly,
with
there are two
those,
things involved. The speed and memory is important.
Yes, for sure.
You are using.
I mean, you
so
can also do super small devices.
Thanks.
Remember the quality that I'll just mute you so that there's no echo. So the quality of inference. So an inference is actually almost everything. I don't know how to explain. Inference is how your model, all models just predict, and they predict a probability that I've recognized some sort of item. So it depends on the quality of inference you are. And then if you're doing something with something or high data bandwidth thing, if you're doing something with media, it's going to be difficult. And that's exactly why we chose our project to be using raw sensor data, where we're using almost numerical data so that we can run this on the smallest device possible. So remember, how big is a buffer going to be if you have to buffer an image so that you can show it to a model, so that the model can compare it to all the other images that it has? Do you see how that sentence is just becoming more and more and more and more data, So if that makes any sense. No, we have not tried edge impulse yet.
So I actually think that this may be a good place to go with this project. And, obviously this is a suggestion, but, Edge Impulse has a community version. And I think that is something that would potentially be interesting over time, is sort of branching this and seeing if we can get it up and running on Edge Impulse, because that is becoming one of the sort of de facto frameworks to use to accelerate commercial grade builds. What do you think about that, Zach?
Oh, I'm just looking at it. So yes, Edge Impulse can run on microcontrollers. I think it would be very interesting to see them, to compare them and see which one is going where.
I actually tried this week to use Edge Impulse with ESP-CAM. Yes, actually, it seems to be much easier process. But until now, I have some difficulties. I don't know, because of my ESP-CAM or because of the Edge Impulse itself.
No, Wafa, it's completely normal. I don't think running AI on microcontrollers is as straightforward as everyone puts. It's almost like I don't know if Drew is here. Running a standalone Zephyr.
It's also like
Yes.
really rarely used. Like me and Jack today, we are finding for resources, and the latest resources we found, it was 4 years ago.
Yeah.
Yes,
So
it's
it
really
is
limited
really
resources.
Yeah.
So here's a question. We have obviously, for those of you who've been paying attention, we are working on a remote platform. And, one of the things that what the purpose of this remote platform is to allow people in the community to run code on embedded hardware targets, obviously remotely. Now we've been looking at building in a CI/CD pipeline, and Dojo 5's embed ops integrates already, I believe, with Edge Impulse. So I'm not sure, like Wafa said, she's not sure if it's the SD card or if it's Edge Impulse itself, but it may be worth having Wafa give it a go.
It is.
Yeah.
It is worth it. It is worth it. But I have this feeling the degree of difficulty changes because I think I've looked at Edge's 5s, and don't hold me to this, but I've looked at it, and most people have it such a way that you can run it on Pi. But a Pi is a microprocessor. Just because it's an SBC, people look at it as that's an embedded device. But below Pi is the difficult part. I think with embedded Linux, this would be a straight shot 15-minute thing. Like really, with embedded Linux, it would go like so quick. So we should try it. We should try it as far.
Even we can, in case of embedded Linux, we don't need even any build tool. We can just run them natively.
Exactly. So it goes so straightforward. But we should try it on. I'm trying to see if Edge Impulse in Dojo 5 runs on what. But I think Wafa, since Wafa has already tried, and also Wafa has a lot of experience with JAX and what's the other one you were using last week? The other time you're using YOLO 5 and well. So I think Wafa is in a very prime position to tell us what model framework or what model tool is the best, because I've seen she's used it in the last few weeks. She's used like 3 or 4 of these tools to quite some.
For microcontrollers, it's like use the FOMO mobile nets framework to train the models. It's like it's like models to train for microcontrollers specifically, especially for object detection and classification.
Which one is that? Edge Impulse.
FOMO, yes.
So here in the so I just dropped an article from Dojo 5 about medical device machine learning with Edge Impulse.
Mm-hmm.
There's just a paragraph here. Not only do we enable our users to build the model architecture, build custom digital signal processing, we can also reduce the size of deployment through optimization for the given deployment architecture, such as Int8 for microcontrollers, or further reduce our additional compilation steps with our Eon compiler. So, it does seem like maybe setting Wafa down this path could be worthwhile. maybe we just reach out to Joe and see if there's somebody there who can help, like on a support standpoint. And Wafa, if you want to discuss in the general chat, like what the project, scope your project, right? Scope it out a little bit. I think it's basically just this project, exactly the same, just running on Edge Impulse, right?
Yeah. Yes, absolutely.
Okay.
Yeah. Oh, so int 8 is Taj will have fun. Int 8 is a flat buffer as well, Taj. Yeah, that's the problem.
Not fun at all. It wasn't fun.
Yes, let's try. This is I think this is a very widespread problem, and I think this is a very opportune moment for devs to tackle something everyone is struggling with.
Just we have to make it work out just once, and after that we are good to go for any model and anything.
Yes.
Okay. So what I would encourage you to do right now is so Wafa, you're going to be the primary, it sounds like. If you can put a little bit in the general chat, like this afternoon for you, like, hey, here's what I'm going to try to do. Here are the different repos that I'm sourcing. And, I think I put this in here, but there's a community version of this. You probably already have it. But for those of you who are interested in participating, there's where you go get the free version of Edge Impulse. So we've got the repos, we've got the Edge Impulse framework. I'm going to reach out to Dojo 5 and see if they can get us somebody at Edge Impulse for support. And so Wafa, if you can scope out a little bit about what you're planning to do, this should be interesting. And then Zach, while we're working on the remote platform, hopefully we can get that microcontroller up and supported in the next month or so. By the time Wafa's done, and see if other people can deploy to the ST.
Oh, yeah, for sure, we can do that.
Yeah. Yes.
That shouldn't be a problem. I mean, these are all parallel efforts that are actually inching forward really well, so it's fine.
Okay. Cool. Well, now we're 15 minutes overtime. So does anybody else have any other questions or anything that they'd like to contribute or figure out or ask? Thanks for the thumbs up, whoever threw those. And now we're going to throw some deuces. Appreciate all your guys' time. We will see you in the server, which again, for those of you who have not participated, you can find us all at https://discord.gg/devheads. And actually, for you guys who are here today, we're not completely done with this. There's still some tiny bug fixes going on and some updates, but the website, the DevHeads website, is up live. We're not like promoting it fully, but you can go to devheads.io and find what we've been working on. Essentially, what we've been trying to do is integrate the functionality of Discord. This is why it's taken so long. We've been trying to integrate the functionality of Discord with a website that is also indexable, so that way a lot of other people who are searching for problems that we're working on can find what we're working on as well. The remote development platform that we've been referring to will be available via obviously the Discord server too, but via the website. There are a couple other cool features and tools. If you're more of a web user, feel free to poke around, and then we'd really appreciate your feedback. If something like doesn't work, obviously let us know and we'll fix that. If something doesn't make sense, or if there's something that you're missing or that we're missing that you'd like to see there, go check it out and then drop us a line, because this is something that we've been building for everybody, and if it's not working for everybody, we want to make sure that it is. So anyway, that's lots of balls in the air, but all moving in a good direction.
For sure. I like it already.
Oh, well, I wonder why.
I see a job. I see for hire as a second post. I like that.
Oh, actually, yeah. Speaking of that, we're one of the things we're doing right now is integrating a page based on our partnership with Webster and Webster. Webster and Webster is a technical recruiting company in the embedded and IoT space specifically. They don't do anything outside of embedded and IoT. So we're integrating their job feed with our site, and then doing a little bit of so it's an RSS, so we're doing a little bit of manipulation on that. But there should be a nice stream of opportunities, both in person and remote, for members of the community to be able to apply for. So yeah, that's all on the way. But we appreciate you guys being part of the community, and we hope to see you in the server/site and back next week.
Cheers, everyone.
All right. Have a great weekend, everybody.
Bye.
Bye.